This is a dynamic programming video on the rod cutting problem. You should have already watched the Fibonacci sequence video before you get to this one. We'll go through the steps set up in that video for this simple optimization example. Let's jump right in and define the problem, hopefully in a completely natural, non-awkward way. So you've got this n-inch long steel rod, and you want to sell it for as much as possible. You know the prices of rods of integer lengths, and you have a machine that can cut your rod to whatever integer lengths you want. So from the last video, we had this framework for dynamic programs, but we got to skip the first, most important step. Here, we need to think of a good way to recursively break down the problem. If you haven't designed recursive programs before, this is probably the hardest part. We want to break the problem down into smaller, similar looking problems. For this problem, how do we break it down? The only thing we can do is either sell the rod whole or cut it somewhere. If we should cut and where we should cut are the only first choices we can make. If we decide to cut, we end up with two smaller rods and each looks just like the original problem. We want to maximize how much we get for each of them to maximize how much we get for both of them combined. The fact that those subproblems look just like the original problem is key for dynamic programming. A slightly different way to think about it is to pick a length of a rod to sell, cut a piece of that length to sell whole, and then recursively figure out how to cut and sell whatever's left after that. Those are two possible approaches. You can make either work. For the second approach, we can even consider another variant. What's the longest length to sell? Of these three possibilities, I'll use the second here. The last two both have a clean visualization and a solution with one recursive part instead of two, but the second one has simpler parameters. In the next video of the playlist, I'll show an example which considers several different approaches for one problem. So we use the second approach, and while you're trying to figure out how long that piece you cut off should be, you hear a divine voice from above.
Trust me on this one. You should definitely sell a 2-inch rod.
That would be great. You cut off the 2-inch rod, get whatever price it sells for, and then you recursively figure out how much you can get for the remaining n-2 inches. You don't try to algorithmically solve that smaller problem. Once you get something smaller than the original problem, you just assume that recursion magically solves the remaining instance for you, as long as you have a base case, which we'll come back to.
Wait a minute, I made a mistake. I meant a 4-inch rod, not a 2-inch rod.
Okay, the voice isn't so divine, but that isn't a problem. We can reformulate our answer to cut off 4 inches instead of 2 inches.
Sorry, did I say 4 inches? 7 inches. Take it to the bank.
Did I say divine? I meant flaky. You hear a flaky voice from above, and it tells you how much to cut off. No matter what amount you want to cut off, you can have a solution that looks similar. In general, you make the first cut. Let's say you cut off I inches. That leaves you with a length I rod to sell, and a remaining length n-I rod to recursively solve. So how do we figure out I without the help of our flaky friend? Just try them all. For every value of I, from 1 up to n, figure out how much you could make by selling a rod of that length and then recursively cutting up whatever's left over. We don't try to get smart with our first cut. I'm not clever enough to know where it should be, but we can try every possibility. Even more importantly, once you recursively have a smaller problem, just assume that it's solved for you. Don't try to do anything with it except think of your base case. The simplest base case here is just a length 0 rod, which is what you get if you sell a length n rod first, leaving you with 0. That's all you will need. So with that, we can write down our recursive program. Don't try to do too much when you start. Just get a working answer first. This is the hardest step. Do it simply, and don't worry about efficiency yet. That comes later from the dynamic programming framework. So great, now we have a simple recursive program. Let's see what that looks like if we run it on a small sample problem of length 5. So each node tells you the length of the rod, and it stores the best answer it's seen from all of the possibilities it's tried so far. When it finishes, I put the final value on the edge leading from that recursive call. Even in this small example, you can see that we solve the length 2 rod 4 times. We hit that 0 leaf 16 times, once for each possible way of cutting the rod. At each of the 1-inch marks, we can make a cut or not. So for a length n rod, there are 2 to the n-1 possibilities. While the tree for a rod length 5 isn't too big, for length 7, it starts to look a bit crazy already. But when we think about what the recursive calls look like, there's only one changing parameter. How much do you have left to sell? And that number is always an integer from 0 up to whatever you started with. So it can't have that many values, just a linear number of them. That tells us that we can make a table to store the best price for every possible length to move to a memoized version. Before making any recursive calls, you just look at the table to see if you've already solved the best price for this length rod. If so, don't recompute the answer, just return it. If not, recursively figure out the answer, but store it before you return it. The code is almost exactly the same as before, or we can clean it up a little. Now, if we look at the same recursion tree for length 5, we see what happens. Like our first memoized Fibonacci version, every node that isn't on the left spine of the tree has its children pruned because all of the values get computed on that spine. We store a linear number of answers and our computation goes much quicker than before. Larger sizes can give you a feeling for the new tree shape. So now we have a memoized version. Thinking about the table, what order does it get filled? In order to fill in any box, we will directly depend on all of the boxes to its left because it directly makes recursive calls to all of them. So there's only one way to fill in the table, left to right. We can write code to do that directly without the recursive calls. We can also think about how long it takes this code to run. To fill in the ith position takes time I because you consider the maximum of I possible first cuts. And we're solving for problems I equals 1 up to n, the full-size rod. That's n squared time, much better than the exponential time we started with. Moving to the last step. Unlike the Fibonacci sequence, I don't see any way to optimize the space for this answer. But we do see the last stage of dynamic programming that was missing in the Fibonacci problem. Generally, you aren't just looking for the price you can get, but also the cuts you need to get that price. It would be pretty frustrating if you knew how much you could get, but not how to get it. So we'll store some extra information to reconstruct the cuts we need. In this case, I'll make a second table. When we optimized over different possible first cuts, I was storing the amount I could get, but I also want to store which cut I used to get that amount. It gets updated whenever the optimal price gets updated. When I finish, that table lets me reconstruct the cuts I need to make. In this instance, if I have a length 8 rod, I should cut off 2 and sell it, leaving me with 6. The table tells me that for 6, I cut off 3 to sell, and then the remaining 3 also gets a size 3 rod to sell, leaving me with 0, and we're done. That completes the problem. We ended up with a quadratic time, linear space algorithm that will be able to reconstruct the answer quickly in time linear in the number of rods of your optimal solution. It's a relatively easy problem with only one dimension the way we solved it, but it's a complete, legitimate dynamic program. We'll see more complex problems in later videos on the playlist, but right now I have to retreat to my secret lair.
Get out of the basement!
Mom, it's my secret lair!